Hi, today we are making this fire simulation effect using Blender's simulation nodes. We'll create some points, add velocity to them, add some curl noise. We'll calculate their normalized age to change their color, scale, rotation, and etc. And also, we'll do sprite sheet animation. It's a lot, so let's get started. Let's start by adding a mesh plane. This will be our geometry nodes object. Create a new geometry node setup. You can also do that by adding a geometry nodes modifier from here. We don't need this group input node, so delete it. Shift A and let's add points node. We can use this node to create a bunch of points. Let's start with 100 points. Right now they are all in the same location. That's why we see only one. You can keep it this way, but I will randomize their location just a bit. For that, drag from here and search for random value node. This will give each of our points a random position. Let's change the minimum x and y to -1 and 1. I keep the set values at 0. This way, we can spread our points along the x and y axis. Now I add a vector math node here and change it to either multiply or scale. Let's use scale. Now by changing this scale value, we can change the spread of the points. I keep it at around 0.1. And just like that, we have our particles or points. Now the fun begins. Blender 3.5 Alpha introduced a new branch a few weeks ago, simulation nodes. What it does is it allows us to run loops inside our geometry nodes. This has opened so many possibilities to create crazy looking stuff which were either impossible before or really difficult to execute. Still, it is in its early days, so expect some changes if you are watching this video months after release. Right now, I am using the December 23rd, 2022 build of this branch. So, Shift A under Simulation, add these simulation input and output nodes. Make sure, as this one says, to add the output node first. Now you can see it has this frame between the input and output nodes. This is where our loop will take place. Make sure you plug our points into this geometry input. If you see nothing in the viewport, just scrub the timeline header and bring it to frame 1. This is another thing you need to remember at this point in the simulation nodes. Let's say you did something in the nodes and it is not working. Don't panic straight away. You may not have done anything wrong, so just bring the timeline header back to frame 1 to see the results. If you're still not seeing the results, then you can panic. To create the effect, our first step will be displacing these points over time. In other words, adding velocity to each point to go up. In geometry nodes, we use geometry set position node to displace anything. Let's add 0.01 to the Z axis. Why such a low number? Well, because each frame this part of this setup will run. That means it is going to add 0.01 displacement to the points every single frame. Let's play this. I set the frame end to 150 for this tutorial. If I add a big number, these points will launch into the Blender space. Just like that. So let's keep it at 0.01. Right now, all of our particles go up at the same time. I want them to go one after the other, one particle at every frame. For achieving that, I like to use attributes. First, I will create a new store attribute node before the simulation input. Set data type to integer and let's call it something like spawn number. Set it to 0 for now. Then I create a logic for our selection socket in setPosition node. I add an input index node to access the index of each point. Then add a name attribute node. Set it to integer and type our attribute name, spawn number, or just copy paste the name from here. I drag from here and search for less than or equal node. Plug the attribute here. Plug the output into selection socket. Now, if we play, you can see only one point is going up. That is because right now we have 100 points which have their index going from 0 to 99. Here we are saying only to add velocity to points which have an index value less than or equal to spawn number, which is 0 at the moment. There's only one particle which satisfies that logic. Let's improve this logic like this. After adding the velocity, we can increase the spawn number attribute. So I add store attribute node. Select spawn number. Add a name attribute node and select our spawn number. Then add utilities math node and add it to spawn number. Let's add 1 for now. Drag from the output and put it here. What we are doing here is, in every loop, we are adding 1 to our spawn number, which increases the amount of points that become true to our previous logic. Let's see it in action. If you're familiar with programming, you can think of this logic like this. We declare a variable named spawn number at the beginning. And in the update function, we check if the index is less than or equal to that variable. If it is true, we add velocity to that point. After that, we say spawn number plus plus or spawn number equal spawn number plus 1. Actually, this number we are adding is basically the spawn rate for our simulation. If I want 10 points to go up at once, I set this to 10. You can set this to 9 if you want the start frame to spawn 10 points as well. Right now, I keep this at 0 and this at 1. Our points are just going up. I want them to have some noise to their flow. So, let's add that. Again, it will be setPosition node. Let's call it curl noise. Drag our selection to this one as well. To add that noise, I add noise texture. I set the scale to 0.3. Noise texture outputs positive values. But I want the particles to move in both positive and negative directions. So let's drag from here and search for map range node. Here I set the 2 min x and y to -1. I keep set at 0 because I don't want particles to go down. Drag the output to offset. Now when we play, we get the noise, but it is too much. So let's add vector map scale node in between to control the noise strength. Right now, all the points share the same noise. That's why you see this trailing movement. We will come back to that issue later. It is time to calculate the age of these particles. We can use this age calculation to drive so many things in our effect. We can delete the particles when they reached maximum age. We can change their color based on their age. Also, we can change the scale, rotation, and all those stuff. But first, we need an attribute to store the age property. I add the store attribute node and call it Normalized Age. Keep the data type as float and domain as points. Soon I'll explain why I call it normalize. To calculate the age of the particles, all we have to do is subtract the index from the spawn number. You can use ID as well. In this setup, both ID and index will do the exact same thing. This calculation will give us the age of the particles in frames. For example, let's say in frame 9 we spawn our 10th particle, which has an index of 9. At that time, our spawn number is also 9. That means the age is 0. After another 10 frames, our spawn number will be 19. But our index won't change. So now the age will be 10. This means the particle which spawned in the 9th frame has lived 10 frames so far. So we have a way to calculate the age. So let's drag it here to the attribute. Now I want to map out this age to a certain fixed range. I want to normalize this age to 0 to 1 range. At the beginning, particles will have an age of 0. When it reaches its death, age will be 1. To create that gradient, we need the minimum and maximum age. The minimum will be always 0, but what will be the maximum? That means we need to tell this simulation what are the life expectancies of these particles before they spawn. Let's say I need these particles to last 30 frames. I add an input integer node, rename it to lifetime and give it a value of 30. Now to map our age to 0 to 1 range, we need a map range node. Drag the lifetime to from max socket. What this does is, it will look at our particle's age and map it to 0 to 1 when it goes from 0 to lifetime value. But I like to have some randomness to the lifetime. I don't want all the particles to die at the same age. To create that randomness, let's drag from here and search for divide. Let's divide the lifetime by something like 10. And this output will be our minimum lifetime. Now I add a random value node and set it to integer. Plug this to min and plug our lifetime to max. Then drag from here and search for mix node. Plug this into B socket and our lifetime to A socket. This slider will work as our randomness. A value of 0 will give each and every particle maximum lifetime, which we specified here. And a value of 1 will give each particle a random lifetime value between its full lifetime and 1/10 of its full lifetime. Values in between will decide the amount of that randomness. This calculation could give us float values with decimals to from max socket. It is okay to have that, but I add a math node here and set it to float to get rid of those decimals. We have finished the basic stuff. Let's organize some of these. Use Shift B to frame nodes, F2 to rename their labels. Hit End to bring the properties panel, and here you have the options to change even more settings of the frames. Now it is time to kill particles when they reach the age of 1. Since we did all the necessary calculation inside the loop, let's use those data to delete particles. Use delete geometry node. Add a name attribute node and use our normalized age attribute. And when our normalized age is greater than or equal to 1, we will delete our particles. To randomize the curl noise to each point, I add index node and divide it by the number of points we have in the simulation. Then I multiply it with normalized age and plug that to WSocket. This will add more variety to curl noise based on particles' age and their index. Now it's time to use Sprite Sheet. To drive our simulation using the Sprite Sheet, first we need to have cards. So, to turn these points into cards, I use instances on points node. Let's use a simple mesh primitive grid for our instances. Let me explain Sprite Sheet animation setup like this. Here I have a plane with this Sprite Sheet texture. A Sprite Sheet is an image sequence of a particular action, but rather than having all those images as separate files, a Sprite Sheet contains all of them in one image file in a grid layout. They usually go from top left corner to the bottom right corner. Right now, this sheet uses the UV space or UV vector to map the texture into the plane. And our goal is to make that UV space fit a grid square and then move it with particles age to give the illusion of an animation. That setup will look like this. Don't worry, we will start from scratch. First, we need a few things. Our UV map. You can use UV map node or texture coordinates node to access that. Then we need a reference to the number of rows and columns in our sprite sheet. Because not all sprite sheets have the same layout. I use a value node for that. The sprite sheet we are using for the fire scene is 6x6 grid. So to scale the UV space to fit one square, first we need to separate the vector using separate XYZ node. Then I take X and divide it by amount of columns we have and divide Y by amount of rows we have. After that, using the combine XYZ node, I combine them back into vector form. You can ignore the Z axis. Now we have a UV vector that perfectly fits a square in our sprite sheet. And right now it is sitting in the bottom left square. Before we start moving our square, take a look at this. When we add an image texture in Blender, By default, it comes with this repeat extension method. What this means is if we scale down the vector, we are getting this tiled look. If I set this to extend or clip, we won't get that. For the sprite animation effect to work, you need to make sure your texture is set to repeat. Because after we scale down the UV space, I am not going to move it along the main UV space. I am moving it on the below tile. Reason for that is the Sprite Sheet usually start at top left corner. So rather than moving our square to top left and then moving it along the sheet, it is easier for us to use the bottom tile. To offset the square, first we need to know the number of cells in the grid. For that, I use math node and multiply rows and columns together. Duplicate that multiply node and make a connection to it. This second value will be our normalized age. We will create a reference for our attribute later, but for now, I just change this value manually. To create the x-axis offset, I take this value and use modulo math node and use the number of columns as the second value. This will give us the remaining value when we divide the first input by the second. This will create 0 to 5 pattern along rows. For example, let's say our normalized age value is 0.5. That means 0.5 multiplied by 36 gives us 18, which then gives us 0 when moduled it by 6. This means when normalized age is at 0.5, our sprite should be one of these. Since the calculation can give us float values, I use a flow math type after this. This will ignore decimals and only give us counting numbers, which by the way also helps to stop the sliding between sprites. To calculate the column offset, take this value and divide it by rows. Then use flow type to ignore decimals. Since we're using the bottom tile as I said earlier, I add 1 to all of these and then multiply them by -1. After that, use a combine XYZ node to make these offset into a vector and use a vector math node to add it to our previous UV space. Actually, here I put it before I scale down the UV space. You can put it after that one as well, but this way we can do the same thing with one less node. Organize your nodes, and here I turn this whole setup into a node group. Extract necessary outputs. You can hit Tab key to go in and out from group node view. You can see it is working perfectly. And by the way, you can use this same method for making Lego faces. Now let's put this into action. But right now our grid has no UVs. So I create a new vector attribute and call it Sprite UVs. Then you can drag this UV to it. If you don't see this for some reason, you can do the same by adding UV unwrap node and plugging it to the attribute. This will create a nice UV map that will work with our Sprite UV animation setup. Let's also rotate our cards to face forward. Create a new material. Let's call it fire. Add a set material node at the end of our node setup and select the material we created. This way we can assign material to our cards. I created a new window over here and changed it to shader editor. In our fire material, I add input attribute node. Copy paste our UV attribute name for cards. Duplicate our attribute node and paste our age attribute name. I believe we have to change the type to instancer. Add our sprite sheet as an image texture. Now add our sprite UV's group node and plug its output into image vector. Then plug other necessary inputs to the group node and enter the number of rows and columns. Since we are not using any color data from this image, let's change the color space to non-color. And now when you play the animation, you can see it working perfectly. Let's work on our material more. Plug the image texture output to alpha. In material settings, set these to alpha blend and alpha hashed. Drag from normalized age and add a color ramp and change it to have flames colors like this. What this does is it gives our flames a color based on their age. In the beginning, it starts with white and then turns to red. Use this as our emission color. For emission strength, I again use normalized age attribute with color ramp and change the starting value to full white and the end value to something like 0.5. Run it through a multiply node to increase the strength. Let's change the base color to black and roughness to 1 and we have our fire material. We are almost there. Few more steps to go. To control the scale of the cards, you can use the scale input in the instance on points node. But I like to do it in 2 steps. Right here, after simulation output, I add a set point radius node. This way, I can adjust the radius of the points. I use normalized age attribute to drive the radius of the points. I use a float curve to adjust the follow and then use multiply node to increase or decrease the scale. Since we set the point radius like this, then we can use radius node and plug that to scale here. You can always adjust the scale to your liking from this float curve. To control the initial rotation of the cards, you can use a few different methods. Use align Euler to vector node and set the aligning axis to X or Y. This will make cards face forward. Then add a random value node to rotation socket and set min and max to something like -2 and 2. To add a bit more randomness, you can duplicate the align Euler to vector node and set the axis to Z and decrease the factor to something like 0.2. I also like to add some rotation over time. For that, add instances, rotate instances node. Then you can use a normalized age attribute with map range node to drive the set rotation over time. Our basic fire simulation is working right, but we got an issue. Two issues actually. One is our simulation only works when spawn rate is set to 1. Whenever we set it to something different like 5 or 10, it is not working. The second issue is our simulation starts decently, but after 30th 40th frame, it starts to flicker. So let's fix those two issues. The reason for our spawn rate problem is the way we calculated the age. So take a look at this chart. When our spawn rate is 1, our starting spawn number is 0, and we calculate the age by subtracting index from spawn number. When we go from first frame to fourth frame, this is how these values changes. First frame, our spawn number is 0. In the second frame, it is 1 and then 2 and 3. Particles that are spawning at that frame are 0, 0 and 1, and in the third one 0, 1 and 2, and like that. And their respective age will be like this: 0, 1, 0, 2, 1, 0, and 3, 2, 1, 0. But if our spawn rate is 2 and the starting spawn number is 1, then this chart will look like this. The spawn number will be 1, 3, 5 and 7. Particles that are spawning will be 0, 1, 0, 1, 2, 3 like that. And their ages will be something like this: 1, 0, 3, 2, 1, 0 like that. And you can see that is a problem. Particles that are spawning at the same frame, whether they are 2 particles or 100, should have the same age when moving to the next frame. That means this should look something like this. But because they have different index, this will not happen with our current calculation method. So here is my proposal. We're going to take our spawn number at 1 and divide it by spawn rate. This will give us something like this: 1, 2, 3 and 4. Then I take our index and divide them by spawn rate and remove their decimal numbers. For example, take the index of 5, divide it by spawn rate 2, which gives 2.5, and then get rid of those decimals, which leaves us just 2. In that way, we get 0, 0, 0, 0, 1, 1 and 0, 0, 1, 1, 2, 2 and so on and so forth. Now if we subtract these two, then it will look like this: 1, 1, 2, 2, 1, 1, 3, 3, 2, 2, 1, 1 like that, which is what we want for our age. So let's do that. Take spawn number and add 1 and divide it by spawn rate. For index, divide it by spawn rate and use flow math node to get rid of decimals. Now to the second issue. The reason for the flickering glitch is how Blender adjusts the ID and index when you delete points. This causes us trouble because we use those two in several occasions in the node setup. Initially, when all the frames are there, our index goes from 0 to 99. But when it starts deleting points which reach their lifetime, Blender will reassign those indexes. For example, when you have 100 points, index goes from 0 to 99. But when you delete the first particle, which is 0, Blender looks at all points and assigns new values to existing points to make sure index starts from 0. Because of this reason, after deleting the first particle, Blender set the index of the remaining 99 particles to go from 0 to 98. But we want to keep their original indexes. This means after deleting the first particle, remaining indexes should be 1 to 99. So let's prevent this by capturing the index before everything starts. I add store attribute node and plug the index to it. Let's call this attribute new ID. Actually, in this setup, both index and ID act similarly. After that, come to where we delete the points and then add set ID node and assign our new ID attribute. This will give those particles their original IDs and indexes, which gonna solve our second issue. So that's it. That's how we made our fire simulation effect. To add smoke and small rising debris to the scene, you can use a similar setup. Just change the values. For smoke, I use this 8x8 sprite sheet and create a new material. For this small debris, you can either use small spheres instead of cards, or you can just scale down the cards to make them look like this. Also, there are few ways you can deal with cards rotation. Here are few more methods. Although it wasn't necessary for this fire simulation, if you like to have the card's initial scale set to not 0, then you can use this setup to achieve that as well. If you like to have a closer look at each of these, all these project files are available for Patreon members. Huge thanks to these amazing individuals for making these videos possible. It has been a bit long video, so I hope you learned something cool, something new. I mean, that's what we like to do. We not only create stuff, we let you create with us. Hit that like button, comment your thoughts below, and don't forget to subscribe to HellFX Learn so you won't miss out when the next video drops. Until next time, see you later.